So let us see the basic assembler functions, how it is converting the assembly code to the object code using the SIC hypothetical computer. So the basic functions are actually converting the mnemonic operation codes to their machine language. Okay, so mnemonic operation, if it is given as STL, then STL's opcode value, it is converted to 14. Then it converts symbolic operands to their equivalent machine addresses. Okay, whenever I'm having labels in the instruction, that references the operands in the instruction that will be converted to its actual address where it is specified. Then build machine instruction in the proper format. Then convert the data constants to its equivalent machine representations, and then it writes the complete object program and assembly listing. So the assemblers function is to convert the source text file to the binary machine code. The directives are start. Usually, the other instructions they will be converted to the opcodes. Okay, but the directives they are giving some other instructions. It will not be equivalently having its equivalent opcode. Instead, based on this instruction, some other action has to be taken. Similarly, when I'm having a start, then it specifies the program is getting started. Okay, so it will not be having its implementation in the object code. It tells that the program starts. Then end, it indicates that is the end of that particular function. Then byte is representing, followed by that byte, we are giving some character or hexadecimal constant. If it is a word, then it represents, it is followed by a integer constant. And reserve byte and reserve word are representing those memory locations should be reserved. That will be used by the function elsewhere in the coding. Okay. So let us take an example assembly program, and let us convert this into object code. So the assembly program, how it looks like this, will be having the address labels. Okay, so the program name is given here as copy. So that is the label given for the program. And then this first is a label somewhere inside the program will be having a transfer of control to this function, this first. Similarly, C loop is the label for this particular line. And since these lines are not having any control transferred in between, they are not having any labels specified. Then in this LDA, there is a reference later. So nfill is given. Okay. So if you see here, we are having nfill here. So this control has to be transferred to this position when there is a jump instruction from there. So we are having the address labels, followed by that we are having the mnemonic opcode, and then we are having the operands. So this is how the assembly program looks like. And this program is actually having the function of reading from an input device and copying it to the output device. Okay, so in this example program, there are two functions defined, read record and write record functions. Okay. So the main routine calls the read record function to read the content from the input device, and then the write it calls the write record followed by that, which writes the content read into the output device. Okay. So whenever we are reading from the record, we'll be using RD command. It will read the input byte by byte, and that will be stored in accumulator. So from the accumulator, it can be stored in any buffer, a memory space. Then from the memory, it will be taking into the final location where it has to be stored. Okay. And when it is having the function calls to be made, it will transfer the control through jump sub j sub instruction. Once the function is getting over, the r sub will be returning to the function where it is called from, to the line where the function is called from. And then when the read record write record is being happening, it will recognize the end of the file or the record using the null character 00. And in this program, we are allocating a buffer size of 4096. Okay, it is in decimal. Its equivalent hexadecimal value is 1000. and the end of file is indicated by a zero length record. Okay. Um, so with this, let's convert the given example assembly code into the equivalent machine object code. Fine. So here the function name is given as copy, okay, and the opcode table is given here, okay, the instruction and its equivalent opcode, it is given in the hexadecimal representation, okay, and the start is a directive, so it need not be converted or it need not be getting into the object code. So the first line starts from here, so that line, the starting address is given here as 1000. So this first line is taken as 1000. Okay, and what is given in the first line? The first is the label. This is actually the label. Okay, then we are having the instruction and followed by operands we are having. This is the format we are having the assembly program. And here if we refer this instruction, it is STL, okay, loading statement we are having. And what should be loaded into the, it has to be loaded into the return address. Okay, so linkage register we want to store with the value, and where should it be stored to? Into the return address. So where is return address? This label is available here. Okay, so when I'm trying to convert this to the machine code, I know STL's opcode value. So STL's opcode value is 14. Okay, so its equivalent machine code will be, for the instruction, for the opcode 14, and the next we are having actually 3 bytes are used. First 8 bits, if you remember the SIC instruction, first byte is used for the opcode, and the next 1 bit, first 8 bits for the opcode, then next 1 bit for index, whether it is indexed or direct addressing, and then the next 15 bits, they are actually the memory reference. Okay, this is how the format should be. So the first byte, it is represented as 14, the equivalent opcode of STL. Then I'm having return address. Return address, I don't know the address of that particular instruction yet, because now only I assign the address for the first instruction. So this is called forward reference. Okay, so since I don't know this value, I cannot fill this value as of now. So when the program is having a forward referencing, it cannot be, the conversion cannot be done in a single pass. So we have to go through 2 passes. So in the first pass, I'll be just assigning the addresses to the statements of the assembly code, and I'll be creating a symbol table. Okay, what is a symbol table? These labels, they are referred as the symbols. So what is the value or what is the address of those symbols? That will be stored in the symbol table. So in the symbol table, let me refer it as SymTab. So now first I have assigned this first as 1000. So I'll be assigning the symbol name as first and its value as 1000. Okay, I'm not having the conversion now. I'm just assigning the addresses to the instructions. And if any symbol is found in that particular line, that is getting entered in the symbol table. So here I'm having a 3 byte instruction. So 14 followed by memory address. And the next line, it will be from 1003. So 1000, 1001, 2. These 3 bytes are used for the first instruction. So the next instruction will start from 1003. So in 1003, again I'm having a label. So this label will be entered into the symbol table and its address is 1003. So whenever I'm finding a label, I'll first check whether that label is already appearing in the symbol table. If it already appears, then I'm creating a duplicate. So it should not be. So error message will be sent. Otherwise, if the label is not appearing already, then this entry will be made into the symbol table. Next, I'm having JSON read record. A function call is made here. So it will be again having 3 bytes. So the next address will be 1003, 1004, 1005. This will be used for this instruction. 3, 4, 5. So the next instruction will be at the address 6. So this LDA will be at the address 1006. And there is no label for this particular statement. So there is no symbol entry in the table. So LDA length, again, this will be using 3 bytes, 6, 7, 8. So the next instruction will be at the address 1009. Then the next instruction JEQ will be at 9AB will be used for, so it's a hexadecimal representation. So 9AB will be used for com. So the next will be at C. Then the next instruction CDE will be used for that. So next will be F. And F, the next will be 1011 will be used for the previous instruction. So 1 to F01 will be used for the previous one. So 1012 will be the address of the next instruction. Next we are having NFIL. So it will be 1, 2, 3, 4 are used for that. So the next line will be 1015. So now I'm having a label. Again, this NFIL, this will be entered into the symbol table. NFIL, and its value is 1015. Then the next instruction STA 1018. Then LDA 89A will be used for that. So B, 1B will be for the next instruction. Okay. And then STA 1001 BCD will be used for that. So next will be at 1E. And we are creating the address, so on. Okay. And once this is created, the equivalent machine code should be created. Okay. Okay, so I'll complete this address reference. So 1E F20 will be used for this. So 21 will be the address for this. Then we are having 1024. Then return sub will be 27. And here byte, if you remember, it is a directive, assembler directive. So assembler directive, this byte will not be having any opcode. Instead, it says that I'm having a constant specified over here. So this EOF is a constant, so that will be directly having its machine representation. So how many bytes are represented? 3 characters are represented. So 3 characters will be having 3 bytes. So here 27 to A, and the 3 bytes will be used for this. So ABC will be used. So we'll be having 2D. And then here 3 words, word 3 integer constant is represented using the word directive. So 3 will be represented here. So again, one word is occupied. So DEF will be used for this. So next we'll be having 1030. And here again, another word 0 is created. So 3 bytes is occupied by this again. So we'll be having 33. And then we are having length. Length is again one reserve word. Okay, so we are not having any values stored as of now, but one word memory is stored. Okay, so this 1036 is kept ready for storing some other value in the program. Then at 39 we'll be having this buffer. Okay, now what is given here? Reserve byte 4096. So 4096 bytes location should be allotted for the buffer. So 4096 is decimal. Okay, its equivalent hexadecimal value is 1000. Okay, so 1000 hexadecimal positions should be allocated or reserved for the buffer. So the next address will be 1039 plus this 1000. Starting from this location 1039, 1000 locations, actually saying 4096 positions will be allocated. So the next address will be 1039 plus 1000. So the next instructions address, this line's instruction address will be starting from 2039. And again here it will start 2039. A, B are used for this. So 3C will be for the next instruction. Then CDE will be used for that. So 3F will be for the next instruction, and it continues. We are assigning the addresses like this. Okay. So whenever I'm having a byte, for example, here we are having a byte, and here how many bytes are given? Only one byte. F will be, it's a hexadecimal. If it is a word, okay, if it is a constant, if you refer here, this is representing constant. So E is one character constant. So E is a character, O is a character, and F is a character. So they will be having its representation in 1 byte, 8-bit representation. But if you refer here, we are having hexadecimal constant. Okay. If it is character constant, for every character 1 byte will be allocated. If it is a hexadecimal constant, one digit will be represented by 4 bits. So when I am having F1, 2 digits we are having in the hexadecimal. So its equivalent representation will be taking 1 byte. Okay, for each we are having 4 bit. For each hexadecimal digit we have 4 bits. So for the total number of digits into 4 will be the total number of bits we require. So since we are having 2 digits, 2 into 4, 8 bits. 8 bits means 1 byte. So if I'm having an address, for example, if I'm having 40 as the address of this instruction, the next instruction will start at 41. Okay. So that should be noted. Other instructions, we are simply adding 33. Whenever we are getting the directives, we have to be careful in calculating the next address. Okay. So this byte, word, these are the directives. So based on the number of values represented over there, we have to increment. If it is a word, no issues, just 3 has to be added. But if it is a byte, based on the number of values represented over, we have to increment the address. Okay. So if this particular line, suppose if it is represented by 2050 something, then the next address should be at 2051. Okay. But the next, since it is a word, 3 bytes, a constant, integer constant is represented. So automatically 3 should be incremented. So the next address will be 2054. Okay. So like this, we are assigning the addresses. So in the first phase, we assign address and we are creating the symbol table. Next, we start converting. In the second pass, using the symbol table, we start converting the assembly code to the machine code. So first we are having STL. STL's object opcode is 14. So 14 is written. Then we are having return address. Return address, where is it found? It is found at the location 1033. So I'll be having 1033. Okay. And next line we are having JSUB. JSUB opcode is 48. And we are having read record function call. And read record function call address is 2039. As you're seeing here, it is 2039. So we'll be having 2039. Then we are having LDA. LDA's opcode is 00. And the length where are we having here? And its address is 1036. So 1036. Then compare opcode is 28. 0 is found at the location 1030. Okay. And we start converting like this. Okay. And when we are having this byte, so for the other instructions, the opcode for the instruction and the value of the labels will be referred from the symbol table. Okay, since the symbol table is storing these values, it will be referred and written over there. But when I'm having byte is a directive, right? So when I'm having a byte, here I'm defining a character constant EOF. So the E's ASCII value, O's ASCII value, F's ASCII value will be taken here. E's ASCII value is 45 in hexadecimal value. So E is 45. Then O is something around Okay, F is actually 46, and O is based on this order. O will be having its representation. So the machine instruction, machine format, that ASCII value will be taken over. That will be getting replaced. That will be replacing this EOF here. Okay. Similarly, when I'm having word 3, so word 3 is integer constant. So 3 we are representing. So 3's hexadecimal representation. So 3's hexadecimal representation will be this 3 only. But using 3 bytes, the integer constant will be represented. Similarly, word 0, using 3 bytes, the integer constant is represented. Then we are having reserved word. There is no word assigned now. This memory is reserved for later purpose. Similarly, next word is also reserved. Then again, the next is also reserved bytes. Okay, so there is no equivalent machine code here. Those memory addresses are reserved for later usage. And similarly, it goes. Next, we are having here STCH, store character buffer X. So for STCH, we are having the opcode as 54. Fine. Next, we are having buffer X. It is an indexed addressing, right? So X was loaded with some value, and that should be used for referring the addresses. Indexed addressing should be done. Mostly it will be used in the array kind of representation, A of 0, A of 1, A of 10, like that we'll be having, right? So in that, it is used to refer the next values in a continuous memory location. So here to represent this, when I'm using the index register, this X bit will be. So first the 8 bits for the instruction, next to 1 bit is for X, right? Since index register is used, this bit will be set to 1. Earlier for other instructions, it is set to 0. Now since indexed is done here, that bit is set to 1. And then we are having buffer, and buffer address is 1039, right? So here we are having 1039. So its value will be now added with this. So 1039, its equivalent binary representation will be, each digit will be having its binary representation for 4 bits, right? When you are having a conversion from hexadecimal to binary. So 1 will be represented by 001, and the 0 will be represented by 4 zeros. Then 3 is represented by 11, and 9 is represented by this. Okay, so since now I'm having this as the information, this 1 bit is for indexing, whether indexed or not, and the remaining 15 bits are for address 1039. Now this total has to be represented here. So now what I'm having, 1001 as the first 4 bit. What is 1001? 1001 is 9. Then 000, then 0011, it's 3. Then we are having 10101. So it is 9039. These are the things you should know down. Okay. So when we are having the indexed addressing, the index bit should be set to 1, and representing the binary value for the hexadecimal, the accumulated hexadecimal conversion should be done when we are converting this index registered instruction to the object code. Similarly, the same thing should be done for this also. For LDCH buffer X also, the similar way the conversion should be done. So by taking care of this, here we are having the final conversion by assigning all the addresses. Okay, for F we are having for O we are having the equivalent hexadecimal value as, machine format as 4F. Okay. Fine. And this conversion is done, and here you are seeing how this STCH buffer X, that is getting converted to the object code. Fine. So when we are having the forward reference, single pass would not be enough to convert it to the machine code. Okay. And finally, once this conversion is done, how the object program should look like is, it will be having 3 parts: header part, then text part and end record. In header record, we'll be having the first column. Each character is very much specific. Okay. So the first column will be having, first column is the first character will be having H, and the next 6 characters from second to 7, column 2 to 7 will be having the program name. So first column we are having H, and the next 6 characters are for the name of the program, and then it is having the starting address of the object program. So starting address is 1000, and then followed by that length of the object program and bytes. So when we are generating the addresses for the next instruction, the program counter that will be storing the next addresses. So when it reaches the final instruction, when it reaches the end record, the end final value created minus the starting address. So that will be giving us the total length of the program. So this should be available in the header record. Then we'll be having text record. So to specify every records specification difference, to differentiate them, header record is starting with H, and the text records are starting with T, and end record is starting with E. Okay. And end record, it will be having E followed by the first executable instructions address. So first address is 1000 it will be having. Okay. And the text record, in each line we'll be having some number of representations. We have converted the instructions to the object code, right? So that we'll be having here. So in the first column we are having T, text record, and then the next 6 columns, it is to have the address of that particular, the starting address of that particular line's object code, and then the next 2 bits represent, 2 characters are representing the length of the object code in that particular text record. Each line is a text record. Okay, so in that line, how many bytes are represented? So that is represented in the next 2 bytes, 2 digits, and then we'll be having the object code. Okay, so object code representation will be having from 10 to 69. The program length may be more than that. Okay, so maximum 69 we can have, and minimum 10 we can, up to 69 we can have the object code. If it is exceeding that, we'll go to the next line, and it is not mandatory that every line should have that much. Whenever we are having a memory break, okay, for example, if you see up to 1039 continuously we are having the up to 1030 we are having the representation continuously. Then from 1033 onwards, we don't have any equivalent machine code here till 2039. Then only we are having the next values. Okay. So when we are having such a break, when it is not continuously available, when the new address, the next instruction is having the new address, we'll go for the new text record. Okay, even though we haven't covered up to the column 69, the text record should go up to 69 column. But when it is more than that, then we'll break that text record and we'll create a new text record. So it starts with 2039 again, and continuously we are writing it. So whatever is converted here, starting from 141033, we start writing it here. 141033. This representation is used to separate between the lines of the original assembly program, but usually it will not be represented in storing the object code. And the next 3 bytes, they are separated by this symbol. Okay. And finally, we are having the end record. Okay. So this is how the assembler converts the assembly code into the machine code in 2 passes when we are having the forward referencing. And if there is no forward referencing, only we are having the backward reference. Backward reference in the sense, here when we are having 0, LDX 0, the 0 is available before then itself. This is backward referencing. 0 is already there. I would have created this address already before I come to this particular line. Before I come to this line, that 0 address would have been already generated. So I can refer that. That symbol table would have been created already. So you can directly get the value from there. So in that case, we need not go for the two passes, but if there is at least one forward reference present, then we have to go for the two pass assembler. Okay, so this is what the function of uh, assembler in converting the assembly language to the object code. Thank you.